In this video, we're going to focus on global extrema in a particular scenario where we have a closed and bounded domain. Just a reminder that closed means that whatever domain we're considering includes its boundary. So imagine some region like this, we would include the points on the boundary. And bounded just means that it is actually something that we can enclose and it doesn't go off to infinity. Say a region that's rectangular in shape but goes out all the way towards infinity. That's not something we're going to consider. This would be allowed. So what does it benefit us to look at this kind of particular subproblem? Well, if we have a closed and bounded domain, we can guarantee that the global extrema of the surface over top of this region is going to occur in one of two places. One, on the boundary of the domain, so somewhere along the edge, or if it is in the middle, it's not going to be random places. We're going to be able to identify those locations by looking at the gradient of f, or specifically looking where the individual partial derivatives of x and y both equal 0. That's going to define interesting points in the interior of the domain. We're going to look at some graphical examples here, and what we see is that there is a boundary around this domain. The words indicate that we're not allowed to go outside of this region, so we're interested just in this part here inside the square. And we can usually identify the local maxes and mins, local, emphasize, in these pictures by looking at these concentric type contours. For example, here we have a contour at height 60, and then 70, 80, 90. We end up with a contour above 100, and in the center of all of that, there is going to be a local maximum. Likewise, there's a series of concentric contours here that lead up to a peak here, and we know it's a maximum because of the numbering on the contours themselves. Last but not least, there's also a point at the interior of those circles, but that is going to be a local minimum because we can see that we're going from height 40 down to 30, down to 20, down towards a valley. From there, we can take a look at the contour heights and identify this 100 as being higher than the points around here. And so this looks like it's our global max. We will confirm that in a second, but that would be the highest single point on this entire region. This point here is a little bit lower, looking at the contour heights, so we're going to have of the two local maxes in the interior, this is going to be the one that shares the global max property. Since there's only one local minimum, it looks like that's going to be the global minimum. Now, we also mentioned that the boundary is a possible location for maxes or mins, but as we're going to see in other contour diagrams, there's no characteristics of the contours along the border that would imply a highest or lowest point. And we can see that for sure here. This contour is at height 40, this contour is at height 50. So this whole region here is z values or f values that are between 50 and 40. Well, we know that these ones are above 100, so 40 and 50 is not going to have a global max in there anyway, and the minimum is around 0 for f, and definitely 40 to 50 is not in that range. And if we continue around the rest of the border, this interval here is between 50 and 60. Again, there's no extreme values. There's a little region here where it's above 60 into 70, but nothing above 100 and nothing below 0. So that confirms that both of our global max and min points here are in the interior. And as a little reassurance, they would represent contours that are single points. And if the contour is a single point, then I can't find a direction that's perpendicular to it. And so we have this condition that the gradient would be a 0 vector at those single highest points in both those locations for the global max and global min. We now consider another example where, again, we limit ourselves to the boundary and the region in the interior. And we're going to look first for local mins or maxes in... Oops. Let's try that whole page again. We now consider a similar problem, just with a new contour diagram, and we're asked to identify the local min. One more time. Get the emphasis right. We now consider the same problem of a contour diagram and then a boundary that we're not allowed to pass beyond. We're going to start this time by identifying the local max and min points. And we quickly realize that there's none of those concentric circle type things. And what that means is that there are no local maxes and mins. We can confirm that just by looking at any single point. Grab a point here. Well, it's at height 130. I can go down this way and up this way. Well, therefore, it can't be the highest point of all the points around it because I can always go some other direction. Another way to confirm that is no matter where we choose a point, we can always draw a gradient vector that says I can keep going up this way, and I can always go the opposite direction, and that'll take me downhill, so the gradient is not 0, 0. Well, that means it cannot be a local max or min. Well, oh, that's it then. What that means is when we look at our global max and min, we will have none in the interior. The only time we can have interior global maxes and mins is if those are local max and mins or the gradient is 0, 0. So that means all the global max and mins are going to be on the border. All right. We scan the border. We're at height 100, 90, 70, 60, 30, 20. Here we almost have that nested idea. We can see that we can push towards the center of this arc here. And we're at 30, we're at height 20, we're going to go down a bit further, and then we're going to go back up. There's going to be some point in there that is going to be the single lowest point on the boundary. Because then we're going to go back to 20, 30, 40, 100, keep going up and up and up. And we can see that as we keep going up and up and up, we're going to end up at this point on the boundary, and that is going to be our global maximum. So in this case here, the global max and mins occur on the border. As a third example, consider the same problem with a new contour diagram. We're going to look for local mins and max points first. We see the concentric circles. We see that the contour heights are going lower and lower and lower. So in the center of that is a local minimum. But that's the only location that has that kind of nested contours. So that's the only local property there is, local min. There is no local max point. Fair enough. Then where we're going to look for our global max and mins is at this point here, which is f around 0. We kept going down. But what about the border? Well, if we look around the border, we're at height 0.1, 1.5, and then we're going up to 1, we're going up, we're going up. So there's a possibility here, f around 2.5, a little bit higher. But then we scan across here, we go, oh, I can go higher than that. So this is not the global max. I can get up to height 3 if I want. And it points to this corner here being the highest point. It's going to be an f larger than 3 anyway. And if I look at other comparable points here, that's f around 1.5. That's not going to be a global maximum. So this, out of all the points we found, is the single highest point that we can find on this contour diagram. And if we recognize that all the other points we saw were all above 0, well above 0, or along the boundary, this is also going to be not just a local, but the single lowest point on the whole domain, a global min as well. So being able to visualize the surfaces and scan around the boundaries, identifying local mins in the interior, local mins and maxes in the interior, that's going to be the gateway to identifying the global maxes in this nice, well-defined, closed and bounded domain problem.